Hey everyone, welcome to
Yes.
this week's podcast
Hello.
on instruction set architecture. And we are going to discuss instruction set architecture and the various kinds that are available in the market, the popular ones, which is x86, ARM, and RISC-V. And then we'll kind of just, discuss more around that. Okay, so diving in, who wants to go ahead and maybe introduce our audience to what instruction set architecture is and why should we care about it?
Well, maybe I'll give it a shot. Yeah.
Go
Okay.
ahead.
Yes. So I would say instruction set architecture is the only thing, perhaps not just the only thing, but the most important thing a software developer should care about when it comes to writing programs. Not the high-level software developers, but the ones who are in embedded, who write low-level software, generally in bare metal or the software which is used to boot up systems. If someone is going to venture into that area or wants to know more about it, the first thing which uh, they should be concerned is ISA. So ISA is like a contract between what software will I write to exercise what hardware, to program what hardware, to initialize what hardware. And depending on what architecture you're writing that software for, it will change. So for example, x86 would have a completely different boot flow, completely different way of initializing systems, uh, completely different way of exercising different peripherals, right? As compared to ARM, as compared to RISC-V, and all of that is kind of part of ISA, I would say.
Okay, so does the
Uh,
ISA also dictate the boot flow, or is it just what the machine can do?
it doesn't necessarily dictate the boot flow, but in the boot flow, let's say we want to enable virtualization, translation from virtual address to physical address. We want to enable interrupts.
I
So
see.
that
Okay.
would the exercising of those peripherals would be a part of ISA in some sense. Like which instructions would you use to enable what peripherals, right? Something like that.
Right.
Uh,
So maybe just so that our
mhm,
audience is able to make sense of all of
mhm.
this. So a CPU would have interrupts some external lines, and the CPU would be capable of doing something by reading the memory. And the instruction set architecture then is the encodings of the instruction that it can read
Yes,
from the
yes.
memory.
Right. Exactly. So it's mainly that. In order to like know more about ISA, we need to understand what peripherals, what registers, what addressing modes that particular processor supports. Right. It's mostly governed by
Hmm.
the architecture of
Okay.
that. I should say of that processor. So for example, ARM A53, let's say. So it would follow ARM V8A architecture, right? And in the
Okay.
architecture spread, you would get all the info about okay, how many registers there are, what addressing modes it support. Now, when we say addressing modes, it's like a sort of way to manipulate. How do you want to reach out to the memory? So where do you want to store
Hmm.
the address? Then if you want to multiply or shift by some offset, that is also possible. That could be one of the other addressing modes, right? All of this is I would say neatly packed into the instruction encoding, which is what the processor core would read and then follow based
Hmm.
on what is described in the architecture. So the arithmetic operations would have a certain set of opcodes. Let's say add. Then what do you want to add?
Right.
Uh, Maybe two registers. You say
Hmm.
what is the encoding of that register would again be described in the architecture. Where do you want to store the result? That would again be the destination register, which would again be the opcode of the register. And in that way, we form
Right.
like complete instruction. Now, the interesting piece, which kind of segregated or defined RISC and CISC was, I should say, load store architecture. So RISC was also called load store architecture,
Well, actually,
where
actually, before that, could you first maybe define the risk, the multiple things actually, the risk architecture, the
Yeah.
CISC
Mhm.
architecture, what are registers, and
Yeah.
what is instruction
So
encoding?
So,
Let's go over the four.
okay.
so
Yeah.
you know what?
Go ahead.
Okay, I will take over this. Okay, you know
Yeah.
what? So risk and CISC comes from the actually it was the CISC methodology that came first, where it was like complex instruction set architecture. The point where the CISC came in, and it goes back to the Intel days, where Intel,
Mm-hmm.
I guess it goes back to 8086 processor something, or
Mm-hmm.
the initial set. And the thing was, software was not very powerful at that time. Compilers were not that powerful. So what people used to like was encode
Mhm.
very high level operations in the instructions itself.
Mm-hmm.
Like you can directly address the memory, you can directly load from the memory, and there's no intermediate. You can do two operations on the memory. Now, the thing is, this may not be true. Internally, they may encode it into simpler instructions, but everything was happening in hardware. So what it means is that compilers can be very simple at that time. They can directly encode into hardware instructions and don't need to do any very much optimizations, because compute power was also not that powerful at that time. But the drawback of this approach is that you end up with very big decoders, because now you have a very big instruction to decode into a smaller instructions.
Right. Okay. So
And decoder, I think, also has to take care of a lot of things, right? The instruction length would be different for each instruction.
Yes.
So decoder had to be smart enough to know, okay, I got this opcode. I know it has this addressing mode. So instruction length would be, let's say, 8 bytes. So it has to, the state machines would keep on changing per instruction.
Yeah.
So if I'm getting, so if I'm getting this right,
go ahead, Piyush.
an instruction essentially is what the CPU would do, or follow to do some action, and that instruction has an encoding, meaning what the bits within that instruction would mean. And you're suggesting that on the CISC architecture, it was variable length. Was that because somewhere the variable length instruction came in? Okay.
It is still a variable length. So depending on what addressing modes there, essentially instruction would have what to do, what needs to be done on what data. Now that data can be in register, can be in memory, right? And how do you?
When we say register, what is a register?
So maybe I'll just brief about it. So what happened is CPU needs some data very close to itself to process it very quickly, right? And the space where we store these values, these are temporal values. We don't have access to it from software directly. I mean, unless you write an assembly code.
I see.
And those space, I would say, is register. It's like collection of D flip-flops where you store data basically. Operate it, and then maybe some point down the line would store back the result in the memory.
Right. Okay.
Maybe you guys want to add something here? In the register.
So you know what, I would like to go back and before we understand CISC and RISC, I want to go back and clarify why we needed this ISA in the first place itself. So when people came up with the idea of reprogrammable computers, the question was, how do you design a system which is ever changing on the bottom and ever changing on the top?
And what is bottom and top here?
So when you are designing a system, the hardware is evolving with time, but the software is also evolving with time. And how do both of them sync up? So I like to think it back into
that's what you were calling the top and the bottom. Bottom being the hardware.
Yes, so the top being the software, and then there's hardware. And what happens when such a situation arrives when you are designing even in a normal software? When you want user not to care about certain implementation, you abstract it out. You say that here's the API, here are the arguments to it. As long as you respect this API signature, you should not care what's happening in the bottom.
Right.
You will get the result as I explain it. And that's exactly what ISA is. ISA is the API of hardware, where the hardware designers basically tell to the software engineers, as long as you generate this instruction, respect this encoding, you should not care what's happening on the.
Right. So how the machine is working
now. So now what they can do is they can change the hardware as well, as long as they don't change the contract, right? As long as the API signature doesn't change, they can do whatever they want. For example, over years, if you go back to earlier days of even Cortex M's, there was no hardware multiplier or hardware divider. And even though there was the instruction might be slow, like multiplier might be multi-cycle. But eventually they were able to spin off a certain design respecting the same instruction set architecture in which a multiplier took only one instruction. It took only one cycle.
One machine cycle, right?
One machine cycle. So that was the whole significance of coming with ISAs, so that the industry can evolve in a better pace. And when it comes to RISC versus CISC, as I said, CISC was a methodology in which people like doing things more in hardware, so that software tools can be easier to develop, which was the need of that time. But slowly we moved in a direction where software tools became much more powerful, and people came up with the methodology, why not have a simpler decoder pipeline and have simpler CPU design? And that's where reduced instruction set came into existence.
Right. So I have one question here, or not question, but a confirmation. So you somewhere mentioned that CISC would also allow doing operations directly in the memory. Like you can take two numbers and add them in the memory itself. Was this related to...
So it may look to there are two things to understand over here. Just because the abstraction says that you give me 2 addresses of the memory doesn't mean it never stores it into the register. What it says is you don't have to store things in register for me. I can
It can do
internally do
whatever.
the same thing for me. So
Right.
you give it 2 addresses internally. Maybe what CISC is doing is, and it may do is, it can divide that big complex instruction into multiple loads into its general purpose registers, add them, and give it to you. And that's where the complex instruction set comes into role. While the reduced instruction set says is, you know what, I don't know what memory is. I will always store in registers. You generate instructions for me in terms of registers. And that's where the whole terminology of load and store comes and gets associated with RISC.
Right. Okay, so let me go back to my question. The fact that CISC allows you to add 2 values in the memory, was that primarily because of speed and the fact that memory access is slow? Was that one of the reasons as well? I mean, if you happen to know.
So it's exactly like, so that software doesn't have to break it. It can, the hardware can internally figure out which memory should I cache it. So right now, even if you have load and stores to memories, and if you look at the disassembly, you will see compilers don't load every value again and again. It figures out during compilation which values might be used quite often and store them in the register and don't replace them.
Right.
So my suspicion is that all that was happening in the hardware in CISC processors when they did memory. So they were caching certain things that they thought might be useful for them into the registers.
Oh, sure. Okay. So you're saying that
maybe I'm wrong. Maybe I'm wrong over here. But to my understanding is first just to keep so that the software tool doesn't have to generate these load stores again and again and manage the registers themselves. They can only play in terms of memory, and hardware can take care of registers.
Understood. Okay. Mohammed, you wanted to
I have
say
a
something?
question. Like, I used to think that the assembly keywords are the instruction sets. So is it true?
Well, not entirely. So the assembly essentially is just a text representation of the ISA, but definitely you will have instructions represented as mnemonics in assembly. So if you have add, subtract, blah 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 instructions as part of the instruction set architecture, those would be available as some form of mnemonics in assembly. That is a given. But assembly need not have just the instructions. Sometimes what they do is they have pseudo instructions as well. So pseudo instruction is an instruction that's not specified in the instruction set architecture, but the assembler will split that instruction into the ISA instructions. So for example, let's say the instruction set architecture has instructions like add and multiply, right? Then what you can do is the assembler writers, the assembly language, the assembler utility writer, what they can do is they can provide a pseudo instruction called MAC, multiply and add. Right, so you can say MAC, then some registers or some memory value, whatever, just a hypothetical instruction. The assembler will automatically convert it into 2 instructions. And when I mean 2 instructions, it's like the encoding for 2 instructions, and it will kind of, in memory, there would be 2 instructions that represent MAC. Right. So I think the shorter answer to your question is assembly language has a representation for all of the instructions in the instruction set architecture, but they can also have pseudo instructions and other facilities so that programming becomes simpler and straightforward. And I'll just maybe add a little more onto the programming facilities. So in terms of programming facilities in C, for example, we have the preprocessor directives, right? The hash include, hash pragma, so on and so forth. So in assembly language also, we have something called directives, which start with a dot typically. So dot section, .org, for example, these are directives. And the assembler gets to know what the programmer wants to do. That's a long story short, right? So assembly language is not only the instructions, but something extra, pseudo instructions plus directives that make life easier for the programmer. Does that answer your question, Wasim?
Yes.
Okay, perfect. Go ahead. Mohammed, you wanted to make a... Go ahead.
Yeah, I have a question. So when you say RISC, is it like the instruction set is simpler and then the number of instructions are reduced, like in number?
Okay. So in terms of the complexity of the instructions and in terms of what they can do, right? They are very simple actions. So for example, add, multiply, these are simple actions, right? So RISC is, as Rajat was mentioning earlier, which is in RISC, you fetch all the values from the memory to the internal registers of the CPU first, then you do simple operations on that, and then you store back the answer to the memory. So RISC is also called load and store architecture because of that. Now going back to your key question, in CISC, for example, if you can multiply 2 numbers in memory, right, So the hardware required for that is complex. The number of actions required for that is very complex in terms of circuit, in terms of action. So what RISC instruction set or RISC machine would do is it will always fetch those two numbers into the registers first, then only perform that one single operation of multiply on the registers only, right? And then store it back. CISC, on the other hand, provides you a circuit to multiply in memory, multiply between registers, multiply between registers and memory. So the multiply circuit itself, fetching data and storing data, manipulating data, that is very complex in a CISC machine, typically. So that's why.
And then the number of instruction was reduced in RISC.
In CISC, in RISC, yes. So the number of instructions are reduced. Yeah.
So
with each
it's funny.
instruction.
So reduced has multiple meanings over there.
Yeah.
So reduced has multiple meanings over there and doesn't directly comply to instructions getting reduced. To what I understand, what reduced meant over here was to so CISC used to have variable length of instructions, and reduced meant reduce the size of those instructions so that they are all of the same size.
Oh, are you
And
suggesting?
that's what
I think it had
means.
to do with number as well, if I believe, because at one point CISC had so many instructions that the RISC philosophy came up with, hey, I'm going to implement only these 50 or 60 odd instructions, which theoretically can suffice to write any general purpose program, but programmer has to be smart about it.
Right. I recall now. I think the instruction set architecture manual for x86 is like 3,000 or 4,000 pages, versus for RISC-V, which is one of the instruction set architecture, I think it's just a couple of pages in terms of specifying what instructions the CPU supports.
So I like to think it in this way, that reduce the instruction set complexity till all of them fit in the same length.
Oh, you're thinking in terms of fixed length instructions.
So let's say you have then you look at a complex instruction and you look like, can I reduce it in a way that I can manage it with 4 instructions separated out, the same instruction, but all of them are of same length, so that my decode
okay. I think fair. So I was thinking of it and my understanding is also along the same lines, which is that is what I was explaining to Dev, which is if you can do a complex instruction, complex meaning it just has too many moving parts. You can say, I'll break it down into multiple actions, and those actions are the new instructions. So
and the only difference is here, programmer needs to know about those actions. Like previously, hardware used to take care of.
Okay, so to summarize, if I need to do a complex, task, in CISC it would take less number of instructions to do that, but in CISC it would in RISC it would take more number. But it would be simpler for me.
Yes.
Okay.
Simpler in what sense?
Like to write those instructions. I understand those instructions in that way.
Your vocabulary has to be, really small.
Your dictionary has to be a lot compact.
Dictionary, not vocabulary.
Right. Yeah.
Like you would need to maybe
the program. Yes. But here the onus is on the programmer to sort of achieve the same thing which previously in CISC architecture, just that instruction would do that for you. Right. Maybe I think one of the examples would help.
Actually, why not do this? Why not do this? Let's now venture into the types of instruction set architecture, and then later on take those and compare and then call out or rather, let's discuss about an example with reference to the instruction set architectures. Go ahead. So let me maybe go ahead and put 3 architectures or propose discussion on 3 architectures. So we have Intel x86 architecture. That's one. When I say architecture, again, it's instruction set architecture that I'm referring to, not the CPU architecture, not how the CPU is designed, not how it's implemented, just the encoding of the instructions. So we have x86. Then another popular one is the ARM instruction set. And then the third one that's coming up in recent times is the RISC-V, right? And RISC-V and ARM are RISC architectures, ISA, and Intel is the CISC architecture. So, okay, with this as the starting point, then who wants to explain or talk about these 3? These 3 or, anyone that you know of.
Okay, I can take up. I don't have much experience with the x86.
Sure, go ahead.
I can however, I can talk about ARM and RISC-V. So, from a perspective of this, I think this, from an instruction set perspective, definitely you have a different vocabulary. But the concept-wise, ARM and RISC-V have a very same methodology, which goes back to RISC architectures. have a simple instruction set that can be used to simplify the CPU design much better. The only difference between them is that ARM ISA is commercialized and copyrighted to ARM. That means if somebody wants to use that ISA, they have to pay some royalty to ARM.
And when you say use that architecture, use in terms of manufacturing a CPU, right? Designing
Yes,
a
and
CPU,
OEMs,
not in terms of writing.
basically.
Okay.
Not in terms of
writing
software.
program.
Yeah, so if you're running a program on the hardware, the company who developed that hardware has paid some royalty to ARM to use their design.
Right. So
Not
let's
their design, their
actually,
instruction set.
sure. Let's actually also talk about ARM as a company, because I think their business model is interesting and people should know
Yes.
about
Yeah,
it.
yeah.
So ARM as a company just designs the instruction set architecture, provides the documents, and other companies are supposed to license that ISA and then go make a CPU of their own. Right? And to be able to make a CPU, design a CPU of their own that complies with the ARM instruction set architecture, the companies have to pay ARM a royalty. Right? And that is where Rajat was mentioning that the one who wants to use that instruction set architecture to design it has to pay the price, but the programmers, it's free for them in terms of writing the assembly instructions.
So there are two models, right? One is where you license just the ISA and you design your own CPU, which is what Apple does. Apple and Qualcomm does. They take instruction. They say that ARM, we will just use your instruction set, but we don't need any of your implementation. The second license is the device license, where ARM itself designs a CPU for you, and you can just pick up that CPU. And that's why all these Cortex M0 Plus, Cortex M4, Cortex R52, Cortex X4, A720, A530 come into picture. These are designed and verified by ARM, and other companies just take these CPU clusters and put in their chips.
Okay. So again, one other thing to clarify here is ARM itself but ARM itself doesn't send the design to foundries and get the CPU manufactured. Test chips is all right, but
Test chips, yes.
test chips is all right, but not at like the mass production.
So they don't make a SoC, or what you call a system on chip. They just make CPUs. And other companies
just
like
one,
Qualcomm,
I think-
Apple, yes.
One addition is their FPGAs, which they do
Okay.
ARM Juno FPGAs, right? Which have the Cortex implementation, which they commercially sell as well, but not the actual SoC, which
I see,
goes
but
into some other products.
but those are like those are the development platforms.
Development
Platforms.
It's just that if somebody wants to start writing their complex software, then they have their CPU implementation, and then along with that there are some field programmable gate arrays, also known as FPGAs. Well, FPGAs are like for different podcast, but the idea is on that you can deploy custom circuits. So you can program your CPUs and exercise the custom circuit. Right.
Yeah.
Okay. Rajat, you were mentioning something.
Yeah. So going back to it, so ARM doesn't sell an end SoC. They do make some SoCs, but those are all for education purposes, maybe vendors testing purposes or some other purposes. But they don't make a end device which actually runs something.
Right.
And so they are mostly so you have architecture license where just people use your architecture and not the device and implementation, which Apple and Qualcomm does majorly. And then you have device licenses where you license the device itself from ARM. In both the cases, you have to pay royalty as well. There's a license cost as well as royalty cost.
Right.
For each device you make, you have to send some money to ARM.
Right. Some percentage.
Yes. So RISC-V is the exact opposite of it. RISC-V started as an open source project where people wanted to say, like, what if ISA can be open and can be proposed and expanded and not owned by a single company?
Right. So actually, I can give a background of RISC-V. So it started off in Berkeley University. It started off there, and I suppose based on what I recall, the professors there decided to write their own architecture to teach the students computer architecture as to how to go about doing computer architecture research and things like that. And the reason for them to make a new architecture was they could not take the ARM or Intel architecture and modify it. If they modified it, they would need to pay royalties to ARM and Intel. Maybe Intel, I think it's not even possible, but ARM, they would need to buy the license, and that was expensive. So they decided to make their own architecture just for teaching purposes. And they took inspiration
Piyush,
from
I have
MIPS.
a question here.
Go ahead.
So while designing the codes, they would not be commercializing that, right?
They
So
wouldn't be
even then you have to
commercializing
pay royalty to ARM if you are not commercializing.
That I don't know. In the sense, what if they decide to, let's say, manufacture one of their chips, the CPUs? Let's say, the university decided that, hey, we'll spend some millions of dollars, send the design over to some fab and get it manufactured. Then,
But if it is not a
you
large
have made
scale, we have made
I
a
think large
SoC.
scale is, I think large scale
It's
is
a
not an
vague
issue.
term.
It's,
And
and
it's a vague
it's a vague term, yes. And I think the whole idea is, if you take my instruction set architecture and make a CPU out of it, you have to pay me royalty. That is how I understand it. I don't think intention of selling it elsewhere matters when it comes to charging somebody.
Okay.
Like
So,
if I
a bit
took
of
a pit,
correction.
go ahead.
Yeah. So a bit of correction over here. So there's no, ARM charges for ISA, but for education purposes, it still provides some of the designs as free. So for example, M3 and M0 plus, M3 and M0 are free for education institute.
Evaluation.
They can pick up a ARM core, do their chip, make it
Right.
for education purposes, but you cannot sell it. It
Right.
cannot be commercial.
I think this is interesting because I think ARM recently did that. I might be wrong. We should fact check
Yeah.
it on the internet. I think 2017 and 18 is when they did
Yeah.
this, and RISC-V we are talking 2010, when it was
Yes.
under development
So-
in the universities.
So if I
University of Berkeley.
understand correctly, then at that time, it was not actually legal to get a design. If I don't know, even if you can get a hands on on that design first, you have to purchase it. But even if you
Right.
got a hand to it and you modify it just in the name of education, that was also not legal prior to.
I think so. Yeah.
Yes.
Okay.
If you are
So-
implementing a CPU, I think the terms require you to pay. But that's my thinking. We should fact check it. Go
So
ahead.
I'm not sure if even if you buy a device license, ARM gives you source code of that device. ARM just gives you binary compiled library of the device
I see.
with the
Encrypted.
I'm not sure.
Encrypted.
encrypted
Yeah, I'm
encrypted
not
something.
sure either.
Yeah,
I mean,
I don't
usually,
think to my knowledge they don't provide the source code of the design.
Yeah, I think that.
I'm curious then. So
well,
ARM
you could
also
pay
has
them
like
infinite amount
OEM.
to pay.
Yeah.
Modifiable.
Also, they have some instructions which are modifiable by OEMs, like the opcode specific
Vendor.
for design vendor.
Yeah.
certain
How
options.
does that implementation go in, right? Then.
I think what happens is you got to pay them more, and they give you like an interface
code as
wherein
well?
I think they give you. I don't know. We
That
should
would be
read up.
very-
ARM's
It's like
website.
Software design paradigms in hardware design, basically.
Yeah,
I don't want to give the libraries, but I want interfaces built so that others can. It's interesting.
Yeah, I don't know how
Yeah.
that works. I really don't know.
So
But go ahead.
but I'm not sure because it may happen there as well, right? What if they, modularize their source code in a way? Because even if you look at your C software, right, a lot of security libraries come as encrypted. As a binary libraries to you, you can just compile and link, not
Yeah,
see
yeah,
their source
yeah.
code. But still, some of them are open, which you can modify and recompile into library. So I think
They must have
Yeah,
something like
something,
that. Yeah.
something.
Yeah.
But I have always imagined
Fair.
it would be very difficult to do that in hardware, because just an instruction requires so much more. Like, in terms of this signal, that signal, I want, info
Well,
about
doesn't
pipeline
that-
latency, this, that.
Sure. So how about your control unit is kind of encrypted, but the interface of that control unit is provided, and some Verilog file just includes who knows. I'm just using the analogy of
Yeah,
the
I mean, we are hypothesizing
code.
at this stuff. At
Yeah,
this
we are
Yeah.
point.
Let's ignore it.
Okay, so cool. Going back to the story of RISC-V then. So it was like a pet project within a University of Berkeley, where the professors and student kind of co-created it to do experiments and learn computer architecture, and they decided to make it open source. So now the first version was RISC-1, then the second version was RISC-2, third version was RISC-3, 4, and then 5. What ended up happening was they open sourced it. And there are like talks on this on the internet, by the way. So my knowledge is coming from there. So what happened was they open sourced it in a hope that anybody out there might want to use it and can make their own processors if they want to, deploy it on FPGAs and whatnot. And slowly, the external, like the open source community, started to make more requests to the professors on the project, saying, "Hey, don't change this architecture now. Can you clean this part? Can you provide one more instruction?" So on and so forth. To the point that they decided, okay, we lost Rajat. Fine, I think he'll be back. To the point where they decided to start ratifying the instruction set. and they have
Sorry,
designed the
Piyush, can you
instruction.
elaborate this a bit more? Like, what do you mean by
Yes. So
ratifying?
the ratifying means that you freeze the
I
encoding
see.
and you say, okay, I shall not change this.
I shall not.
Right. Right. And the ratification kind of takes time. But what they decided to do was they decided to provide the absolute bare minimum instruction sets. Instructions within the instruction set that they would never have to change.
I see.
And so the concept of extension came in. Let me just add Rajat. Okay. So, and then I'll just, yeah, so Rajat's back. So the concept of ratification came in, and then after that, the concept of extensions came in. And this is with respect to the RISC-V architecture. So now what happens is they have different extensions which are just alphabetically named, A, B, C, D, blah, blah, blah. So the most basic and mandatory extension in RISC-V architecture is the integer instruction set extension. If you implement that, if anybody, and you can, go online, get the instruction set architecture, go implement a processor of your own. And if you implement the integer instructions, then whatever machine you have created, designed, that can be called RISC-V. So it's RISC-V compliant. And then now let's say, yeah, so we were talking about the add multiply previously. And CISC machines, Intel architecture having like an instruction for it. So let's say your machine now needs to do multiplication, and it only implements the I instruction set or extension, I extension, RISC-V machine. So either you can achieve the multiplication by recursive addition, or now you can go ahead and modify your machine to comply with the M extension of the architecture. So now your RISC-V machine would be called RV32 or 64, depending on the register width that the CPU can operate on. And then after that, it would be IM, denoting that you are having a RISC-V machine that is 32 or 64 bit and supports integer and multiplication extension. Right? Once you implement the M extension, you also get more assembly instructions, so to speak, encodings. Now you can have multiply as one single instruction. Right? So that is the history and idea behind RISC-V. Right. And then now coming to the x86. So somebody wants to go ahead and explain what x86 is.
Yeah, maybe I'll give it a shot.
Yeah.
So I have not worked much again on x86. I remember my college days. I wrote the snake game in assembly of x86, and there I was snack game. It's snake by the way. Yeah. Anyway, so the first thing which I really excited me about x86 was you'd literally find any instruction you could think of. Like there comes a point while you're developing and you want we are writing in assembly, you would want like, hey, if I had branch less than or equal to, you would have that instruction. You would say like, hey, I want branch greater than or equal to, you would have that. I mean, these are very, very easy examples, but there were some crazy instructions as well, which we'll talk about, at the end of our discussion.
Right.
But here, now stitching to the whole story of a difference between, x86 and RISC, meaning CISC and RISC. I think Rajat put it very aptly earlier, where he said that, why did it evolve like this? Because the time, the need of that time during 1970s when it all started was like such, where we did not have sophisticated softwares to take, a load bear, the stitching of multiple instructions into one, basically, like pseudo instructions, which we just talked about, right? We did not have such complicated or sophisticated software. So responsibility was borne by hardware to implement that complex instructions in hardware. The entire decoding unit instruction implementation was huge. And that is why you would see, that did not leave much area in the terms of hardware to implement spare memories. So when we say spare memory, we talk about generally registers. So you would see in CISC, there are only like 4 to 5 registers available, for programmers.
Right.
General purpose registers are very, very few. Right. A, B,
this
C,
is within
D,
the CPU.
SI, DI. This is within the CPU. Yes. While what happened was RISC came up with a completely different mindset. It's like, okay, I don't need, such complex instruction set. I don't need all of the crazy instructions to be implemented. If there need be, programmers will write, the substitute code, which may not be covered in one instruction, but they would use multiple instructions to achieve that. But my hardware is not going to provide that. So what ended up happening was their decoders, their entire pipelines, their instruction implementation itself got simpler in hardware. which
I
left
see.
more area for registers. So you would have like multiple general purpose registers, which would be, say 32, 64. Some processors even have like 256 registers now.
Right,
And
right.
that is where they proposed the load store architecture. So another thing was also happening in pipeline, right? When CISC came in, if you see the gap between the speeds of processor and the memory, it was not that much. So both
In the
kind of
earlier
went
days, you mean?
in the earlier days, in 70.
Yes.
Yeah.
Okay.
So the processor
Yeah.
would be running in some megahertz. The DDR would also be running at some megahertz. So
Right.
what happened was CISC found it trivial to use memory directly, right, for operations. So you, let's say you want to add two numbers, you get them, operate them in the register, but then store back in the same instruction to the destination memory location. Yes. And that is why caches did not make sense at that point, because you would get ultimately the same speed in memory. Why to have cache? But while the time RISC architecture was evolving, we had seen a clear demarcation between the speeds at which the cores would operate versus the speed at which the DDR or memory would operate. There was a huge gap.
Right.
And now, memory accesses, like 3 or 4 memory accesses per instruction, obviously was costly. So you would have to have a different approach as to how do you, reduce those memory transactions, right? And that is where you see caches coming in play. You would see RISC-based load store instruction philosophy, where you would say, hey, I will load this, keep it in register, operate there, and then when I'm sort of happy, this is my final result, I go back and store. Otherwise, I'll keep playing around in the registers. And if you are implementing load store architecture, you would want more registers at your disposal, which is what RISC-V gave.
Right. So, this reminds me of another important link here, which is the instruction set architecture also has an effect on the compilers, the complexity of compilers.
Yes.
So do you happen to know CISC and RISC, how they affect the compilers? Well, also, let me actually mention this before we go there. Let me mention this, that the compiler is the program that will take a higher level compilable language like C, C++, and then compile it down to machine code that the CPU can understand. Right. So then the idea is, based on CISC or RISC, how does the compiler complexity become? In the sense, is it easy to write the compiler, hard to write the compiler, so on and so forth? So go ahead, Mohammed.
This is a very interesting one, and apparently I would say I'm not so sure whether it would be like, in which case compiler writing would be easier.
Yeah.
The reason is, maybe I'll give some explanation as to why. Initially, it seems like, hey, because everything is done in CISC, like hardware itself is taking a huge load here. It would be easier to write compilers for CISC, which was the, if you remember, which was the motivation why CISC became like this, right? Because we did not have sophisticated compilers back then. But now the issue is twofold here. Okay, so maybe I'll just give one example of how complex the one of the instruction of CISC is. So did you guys know? I forgot the name of the instruction. It's huge. Even the mnemonic is like an essay. Like 500 words. So I'll maybe we'll link the.
We'll link it in the
so that instruction can literally find a substring for you in a string, which is itself a program, right? Which we do in DSA. That is, believe me, that is an instruction in CISC.
CISC. Okay. I think this is where it answers the question that
as to how complex the.
So they implement an entire algorithm with
as an instruction.
As an instruction in hardware.
So I would just like to do a bit of justice over here. So compilers, what actually they do is they never convert a high level language directly into a machine.
Oh, right. They have.
They first try. Yeah. So first they try to represent any kind of language into an intermediate language.
Right.
And they do it for their own modularity, because if you don't do that, you need to write a separate compiler for everything.
Oh, right.
So you want to break down to architecture specific and language specific parts separately, so that somebody who wants a right compiler for a different language can just change the language specific part and still keep using the backend part as same. And whoever wants to just change the architecture can keep the front end part same and change the backend part of it. So
I would like to add some terminology here, which is, in GCC you have the front end and then you have the back end. And backend is machine facing, the one that generates the opcodes, machine code. And the front end is the language facing. Go ahead, Rajat. Yeah.
I guess GCC still doesn't have a very clear clarification on it, but Clang is very. But if you go to LLVM, it is very easy to explain. Where LLVM is actually backend and Clang is the front-end compiler for C, which uses LLVM as its backend.
Right.
So what happens is you try to represent all of that as an intermediate representation, which is a different language within itself for a compiler, and then you take those intermediate representation and try to optimize them. Now, what compilers found it over time is that since they were able to do much better algorithms of optimization, they broke down the intermediate representation to be as simpler as possible. And with time, what happened is that intermediate representation matches well with RISC. So it became easy for them to do backends for RISC than to do backends for CISC.
Understood.
Yeah.
Right. Interesting.
And also, Piyush,
ultimately, if you look at, and if you ever get a chance to, yes, Mohammed.
Sorry, I wanted to add one point.
Okay, I will just complete it.
I think there is a lag here. Yeah, go ahead.
Okay, you go. Yes, okay. So what I was saying is that if you ever look at some of the intermediate representations, they look very similar to a RISC instruction, where you like assign A this, assign B this, add A B, add A C, and then they do optimizations on it. And ultimately, those optimization variables come registered somehow.
Right.
That is the dark magic of the backend optimizations.
This also reminds me of the fact that for the RISC architecture approach, I think David Peterson and John Hennessy, both of them got the Turing Award. Again, I don't recall exactly, needs to be confirmed, by a lookup on the internet. But yeah, the RISC architecture, the idea of it, the load store, they had predicted that doing small things efficiently, faster, would outdo the performance of CISC, the benefits from CISC. And yeah, I see that, what Rajat is mentioning, it goes back to that idea that the intermediate code resembles RISC.
Actually, we are doing a bit injustice to CISC. RISC actually came in at the same point as CISC. So when Intel was, RISC didn't came in 2000s. It came in 1970s. It came as IBM started research on it, and actually the Berkeley was one of the initial projects in 1970s. And as a result of, so they did actually research with two universities. One was Stanford and one was Berkeley. And from Stanford, later 1980s, MIPS was born. MIPS architecture
is
Stanford.
MIPS true, but is MIPS RISC or CISC?
RISC architecture. MIPS was one of the first RISC architecture implementations.
Okay, that makes sense. Right. Wow.
ARM came in very late into picture. ARM came in somewhere in 1990s into picture, but MIPS was the initial RISC architecture for everybody.
Right.
And there were multiple architectures that born out of it, like SPARC, PowerPC, etc. But they never made them into the high performance systems. They always left into the low performance system, because that's where they wanted power. Wherever power was critical, RISC was still getting used over there. But they were not able to make their entrance into the high performance, and CISC always won into the high performance market.
Back then. Right.
Even if you look at ARM got popular because the smartphone industry came in, and smartphone industry suddenly wanted a power over performance.
That
it was the first time. Yes.
This
was the first time.
Right.
Okay,
it reminds me. Go ahead.
So I will just finish it. So this was the first time in the overall industry when people started thinking about power before performance. Till now, it was always performance before power, and that's where CISC was like still dominating the market, and Intel was like thriving in the industry.
Interesting. Yes.
And I guess not until 2015, Intel was still thriving in the industry.
And then, okay. So, while you were mentioning the story or hinting at the ARM architecture, I have to mention as to, how it got introduced in the world. Again, I don't recall all the details exactly, but I think the BBC required or was looking for a computer that could.
They had organized a competition as well.
They had organized a competition, and the idea was who can design a CPU that would fit into an educational computer. And what I remember is, few folks, called themselves ARM, Acron, some RISC machine, something. Again, I'm getting, Acron RISC machines or something like that.
So, Acron Systems. The company name was Acron Systems. It was a British computer company.
Right.
And they went 1983 or 4,
something around that. I don't recall the numbers, the dates. But then they go ahead and implement the CPU. They, create that machine which can be used for educational purposes, so on and so forth. And turns out that then when they were running that, they booted that CPU for the first time, the power cord was unconnected. if I'm recalling the story correctly. And that's when they
Yes.
discovered that it was a very power efficient core that they have created. And I suppose much later, let me just complete, Rajat. So
Yeah.
just before we run into that, you speak. So the Apple folks were looking for a processor for the iPods, and ARM was the one that they picked because iPod was like the battery-powered Walkman device that they wanted to mass produce. And the moment that took off with the
This was also
iPod,
around that time in 1990s.
I don't
iPod?
know. I think the iPod was around before
2000
2007 because
Yes.
2007 is when iPhone came in, and I remember the introduction of iPhone was like an iPod, a phone,
But better.
and a Safari. Yeah,
Yeah.
and three of them in one. But anywho, so iPod discovered or chose ARM architecture as our efficient core, or power efficient architecture, and from there it just went into iPhone, and then others joined the bandwagon, and today it's in laptops and desktop and server chips. So that's the story of ARM then. Yeah. Go ahead, Rajat. I had interrupted you.
Yeah, actually the relation goes back even beyond that. Icon Systems had it even for the Newton processor. The Apple was working with them for Newton processors in 1990s.
In Lisa as well, right? Apple Lisa computer, I think.
Yes.
The first GUI machine.
Yeah, so they were working with ARM a long back. Even Nokia, actually, even before iPad, most of the smartphone industry was using ARM already. Nokia, etc.
I see.
So iPod was like, so ARM was already getting popular across the world. The only thing was it was not getting popularized in where performance was needed, like specifically computers, etc. And that's where Apple led it with M1 Silicon. A lot of people tried to do it with RISC, but never were able to compete with x86. And then Apple did M1, and now people are moving towards ARM for PC as well.
Right. Wow, that's interesting. Very interesting.
Also, Piyush, I would like to add, one important point in the story of how they won that competition. So if I recall, they had sort of.
This is the BBC, the BBC
Econ, the competition which you're talking about. So they'd gotten themselves, a shipment of Hitachi memories which were like double the speed of, the available ones in the market, which were people were using DDR. So DDR used to run at, let's say, 2 megahertz. ARM found themselves with a shipment of memory which was like, they made a deal with Hitachi to get DDRs running at 4 megahertz. That is how they were like, hey, our computer is power efficient as well as performant. So that's how.
But their CPU was slower. That's what you're saying.
Because they implemented RISC, they would inherently need more memory accesses because load store architecture.
So
they needed, they needed memory which were
faster memory.
Yes.
Wow. Okay.
And CISC could mostly achieve that, in lesser instructions basically because
lesser accesses. Yeah, memory accesses. Right.
Yeah. Wow, so I did a small check, and actually ARM was co-founded by Econ Systems and Apple.
ARM was co-founded?
Well, ARM as a company. So before it was called Econ RISC Systems, and when it changed its name to Advanced RISC System, it was a partnership between Econ Systems and Apple in 1990.
Understood. So they got funded by Apple, essentially rebranded themselves or renamed themselves as Advanced RISC
Machines.
Okay, perfect. Yeah. Wow. Great. So now
I think we detoured into
into the history.
It's fine.
Why not? The whole point was to kind of come back to this one question, which is why should an embedded engineer care about instruction set architecture? Why do you guys care? Okay, again.
So I have to. The shortest answer is we have to. It is actually the contract which software has to adhere, right?
So I want to add something like. Okay, so what I find that this ISA is acting as same as dependency inversion. Like higher level module should not care about the lower level implementation. It should depend on the abstraction layer. So ISA is that abstraction layer, and lower level module should implement and follow the abstraction layer.
Correct. So ISA is the abstraction layer between software and hardware. That is correct. Yes.
Yeah. So.
Okay, I think Dave was saying something. Go ahead.
So I was going to ask this question that being a C and C++ programmer, do you really care about what ISA you are using, or like while writing any complex software, do you need to understand ISA of the machine you are working on, or your software you will be hosting on?
So I will put a break on it. So ideally, no. Yes, you should. You don't care, and that's how you have all this application, Visual Studio, or even the stream side or Riverside running, or Chrome browser running on it, because they don't care about which architecture they are running on.
Right.
So the thing is, but do you, as an embedded engineer, when you are developing chips that are going to run the motor on vacuum cleaner or a DSP processor, do you want to care about architecture? Yes. At that time, you very much care, because sometimes you want to bypass this compiler abstraction itself, and you want to directly control directly write those instructions, because they are very critical.
Right.
You know, there are certain things that you cannot do with the C language keywords as is. And for that, you need to write like a function in assembly language that you call from the C language. For example, let's say cache operations. You know, there are specific instructions in the ISA that help you evict the cache, clean the cache, so on and so forth, right? How do you call those from the C code? You cannot. So what ends up happening is you have to write certain assembly functions. And for writing those assembly functions, you have to now know about the ISA.
Yeah.
Should we, meaning embedded engineers, go by heart the instruction set architecture? No. But you should just know how to, look up important instructions, by browsing the ISA. That's about it. I have to give one more example, which is, so let's say you are implementing a lock, like the mutex or the binary lock, right? So how do you go about doing that? You want an instruction that will read and update the memory location in one
cycle.
shot, one machine cycle. Yeah. Well, actually, not one machine cycle, but as one transaction. Like the moment you say
the word could be
right code
atomic
is-
here, atomically.
Yes,
Atomic,
yes, atomically. So you have certain location in the memory that you want to test if it is one or not, and if it is not one, you want to write a one, meaning that you acquire the lock, so to speak. And even to do that, you need assembly instructions. You cannot tell C to
Yeah.
generate, or at least I don't know if it
Specifically,
can be done.
this would be different for different architectures. That is why we
Yes.
need programmers'
Yes.
intervention here. Like
Yes,
the compiler,
yes.
I mean, its compiler is not smart enough to say, we need a log
This is
here
atomic.
to do that. Yeah. So we have to sort of bypass that.
Yeah. Well, what I don't know is if the GCC or Clang compilers provide certain
So indications or
attributes,
hints.
right? Right. Certain attributes that you could mark a variable with, and then access to that variable becomes atomic. I don't know that. But in case you wanted to implement locks, yeah, you got to search for the right assembly instruction, and then go ahead and same with the well, okay, let's go a little deep here. So let's say you're implementing a scheduler, for example, right? So now all of a sudden you have to be aware of the CPU registers, and CPU registers are also kind of mentioned in the programmer's model within the ISA. That's one. And not only that, there are special instructions to touch the CPU registers. You cannot use you cannot use ordinary instructions to touch some special registers within the CPU. For example, there is this MSR and MRS instruction on ARM that lets you read a status register into the normal register of the CPU, and then you can store it to memory, whatever. But going back to the idea of scheduler, to implement a scheduler, what you would want to do is take the entire set of instructions, the entire set of registers within a CPU, and somehow copy them over to a memory region. Take another set of memory region and copy them over as register values in the CPU, and somehow you trick the CPU into executing another program. So things like
why
these
we would need to
require
do that, Piyush? Maybe can you
so that
share
you
some light on
sure. So maybe let's talk about this. So you have one CPU that can only execute like a sequence, right? Single program, top to bottom.
Right.
The question then is how would you go about executing two programs at once? Well, first off, you cannot execute them at once, but what you can do is execute one program for some time, execute another program for some time, then execute the first program for some time, and you can go back and forth. And if you do that like very rapidly, which the CPUs are capable of doing because how fast they operate, the user can get an illusion of two things running at once, right? And then the idea of scheduler is the entity that switches or convinces the processor to execute another program after that time interval. Round robin scheduling, essentially. We could talk about this in great length.
Yeah.
Yeah, another podcast. Yeah.
But I
yeah,
suppose
that's
the reason why we need to copy the data back and forth is because that data in those registers belongs to one process which needs to be kicked out, and we need to
Right.
copy in the already stored data of another process which now needs
Right.
the CPU time. And that is
Right.
where we, in order to implement the scheduler, we would need to be one with the ISA, basically.
Yes.
We need to
yes.
know what
And when we
pieces are changing.
right,
Mhm.
right. So when, let's say, people execute the main function or a.out executable on Linux, underneath what's happening is you're creating like a memory region where the CPU registers can be stored. Yeah, again, that's like a deep topic.
Right.
Yeah. So
That's
so
that.
let
Go
me
ahead.
let me just put it in a very simple terms. You only abstract things which are standardized.
Yes.
Add is standardized. Subtract is standardized. Multiply is standardized. And nobody has a different understanding when you say add. Nobody has a different understanding when you say subtract. But each CPU says, I have a different understanding when you call memory barrier. How can you standardize that? There's no way to standardize that.
Okay. Yeah, that is neat. That is neat.
So
those
that's
kind of
where
instructions.
Yes. So whenever a behavior comes where you want to have such kind of unstandard operations, C doesn't support it. No compiler supports it. And that's the point where you have to venture back into assembly.
Yeah. These are all reasons.
But luckily enough, I think this is not required in that frequent number. I mean, all of these.
Right.
we
Not
say.
that frequently.
So,
Yeah.
If you are a person directly working on processor, then you might. If you are writing firmware drivers, then you won't.
Yeah, typically people who write very low level code, bootloaders, some initialization code, those are the ones who would need to venture into this. And also in general, as an embedded engineer, it's a good idea to know that something like this exists, should take a look at it, just index it, keep it at the back of your head. And and I'm pretty sure somewhere, in the embedded systems engineer's career, they have to deal with startup code somewhere, at some point. Can't just
And that is written in assembly.
yeah.
Yeah. So
There's
I would just
always the
the funny
startup.s.
leave startup.s. So I started my career with the ATMEL.
Uh-huh. Okay.
Okay.
Am I the only one who is
You
not
can
able
switch
to
off your video
No.
if
Yeah.
the bandwidth is not.
I'm just hoping that he's locally getting recorded.
Okay.
Oh yeah, okay. You're muted. Rajat, you're muted. Yeah, go ahead. We can't hear you.
Okay.
Let's just wait. Yeah, this is going to be fun.
Should we laugh at some point just to? Okay. I think
We
he's
can
back.
record a generic laughter.
Okay.
I think
So I guess
Okay.
I'm audible now.
Yes.
I'm audible
Yes.
now.
Go ahead. Yeah. Go ahead.
you
When you were
started
working at
your career at
ATMEL,
ATMEL
Okay.
and then you left
See,
the company.
Then you
or
left.
podcast.
the podcast. Go ahead.
I guess I don't think I left. The company got sold.
Okay.
So yeah. So what actually? Am I audible?
Yeah,
Yes.
and there is a
Yes.
lag.
Hello.
Yeah, there is a lag.
There is a lag, yes.
Go ahead, Rajat.
Maybe
Talk
you wanna
about your
rejoin,
experience
Let's
at-
wait. Hope
Yeah.
my internet catches up.
Yeah.
So meanwhile, people maybe I just want to close on one topic, right? You asked the question of how hard or what sort of difficulty persists in implementing a compiler for CISC versus RISC. So it may seem like compilation for RISC may be difficult because we have to add a lot of stuff which RISC architecture or the hardware eliminated. While in CISC the hardware takes care of things, so compilation becomes a bit easier. But now, with the instructions as crazy as substring finding, the job of the compiler becomes to find that pattern in the user code. Okay, this is what user means here, and I can maybe replace that with substring finding assembly
Right.
instruction.
I think that
becomes
pattern
very tough,
recognition is
That-
complex.
yeah. And I think that was seen in some studies as well as some research done where no one apparently not much code in the existence used those instructions.
Those
You would not find it
instructions,
anywhere. Yeah, they are just there, but no one is there to use it unless you want to actually write assembly specially using that. But
Right,
the crazy
right.
thing now
Right.
is you have to adhere to the software backward compatibility. You cannot now remove that from the existing CISC
That's
architecture.
yeah,
Yes.
that's what puts the CISC architecture in a soup.
So,
Go
so
ahead.
Yes, they
interesting.
can't.
So
It's like there's just
interesting.
one.
Yeah.
I want to add one, apt kahavat here. It's like ugal bhi nahi sakta, ugal bhi nahi sakta, nigal bhi nahi sakta.
Nigal bhi nahi
It's
Can't swallow it,
so
can't. Yeah.
can't
So,
remove it. Yeah,
spit it
go
out.
ahead.
Yeah. Okay.
So interesting question here. Let's say I am doing a DSA question, like DSA interview, and I want someone to implement substring finding, and someone say, okay, what architecture are we running on? And I say that we are running on CISC, and he says that, okay, this is the instruction you execute, and then everything works out. Interview is end.
Yeah, I
Right,
mean it would.
so-
True.
if you are a hardware
It would
programmer,
be out of the box, definitely. Yeah.
right?
Definitely, yeah, definitely. That would be very interesting. I
And
haven't run into
there is
anyone like that
there is
yet,
again
but-
another instruction. Yeah, it's filled with such crazy instructions. Like have you guys seen Harry Potter, where in part 2, where
Yeah.
Full
Voldemort reveals
disclaimer,
himself.
not
He's
a,
like, hey,
not a
okay,
Harry
not
Potter
a fan.
person.
Okay. But I think I'm hoping
Tom
someone
H.
here. Tom
H. Riddle.
Tom Marvel
Tom
or
H.
Riddle.
Riddle.
Yes.
Tom
Tom Marvel or
Marvel
Riddle. And then he
Rid-
swishes his wand and it, rejumbles itself into I am Lord Voldemort. Now you could do
Yes.
that in one instruction in CISC. Believe me, not kidding. You provide the string in as an argument. You provide the bit mask as to, hey, I want to move this character to this position. I want to move this character to this position, and
And
swish.
it'll do it.
It will do it. The intention,
crazy.
I'm like, we would be asking ourselves, why do you even have that? And the reason was, I have some love for CISC because it's crazy. It's crazy to find such instructions. Like you give one instruction, it does it. Hardware takes care for you, and it was there for a reason as well, because they wanted it to convert,
used it.
data from big endian to little endian. That's how
Nice,
you would do
okay.
it, basically. It's like, hey, I'm making it easier. But then everyone changed the rules of the game. It's like, hey, now we'll use little endian everywhere, and that instruction now has gone useless.
Oh, yeah.
Actually, no. So I would just say even ARM has these instructions. They call it rev instruction, rev
They
8, rev
reverse the
16, and
byte.
rev 32, which is
It
used to
would just do
convert between
reverse,
little
right?
and
Yeah,
it is
but
the-
it would only do reverse. Here you can
it is
jumble up
basically
in any order.
yeah. So
It was
they
more
wanted to be yeah. So it's so I would always say this, right? So this came up with instructions where it had no idea how people will use it. While when ARM
Yeah,
came up with
yeah.
instruction, it already had a history of 30 years of people using software.
Right. They could
How
make
people
better
have
decisions.
they could
Yeah.
make better decisions about it.
Right. And I think RISC-V has been able to leverage or stand on the shoulders of giants even more,
Yeah,
and
yeah.
made a lot of more better decisions. Cool. I think Rajat's he's back and now we can hear him well. So do you want to go back to
mean,
your story of ATMEL?
Yeah.
And then
We
So
know
we
he
can
was at
continue?
ATMEL. After that, we lost.
He left.
We lost.
Yeah. So when I started my career with ATMEL, the first thing I worked on was debugging a customer project, which was basically 50 files of assembly code.
Okay, that proves
50
the point.
files, okay?
I think any high-speed application, high-speed meaning, let's say, high-speed trans receivers, right? Ethernet, high-speed I/O, essentially. The code for that would be still written in assembly. And I'm hoping Rajat's still around. We lost him
I
again.
don't think so. Yeah.
Okay, perfect. No worries. But I think the summary is
What makes
that
you say that? What makes you say that? High speed I/O would be in.
Oh, okay. Because I talked with one of the other persons on the team a few weeks back, and in their past life, in their previous company, they were writing high-speed I/O drivers. Some specific, I think, they wanted to check something or something like that for testing purposes. And the processor that was handling the I/O was a little slower than the I/O. And so for those reasons, things were in assembly. Right? The code had to be like as compact and as small as possible. So, yeah. Cool. So I suppose that's that. And, do you have any more questions or comments on? Go ahead, Wasim. Do you have any?
So I want to know, like, if I write a code in C and it is converted into assembly file, can we optimize there by using some tools? So it will make it faster.
Sure. So usually the compilers implement that tool that you're talking about. optimization tool. That's part of the compiler toolchain. But let's say if you wanted to manually do certain manipulations, right, modifications, you can definitely do those. So what you can do is you can, for example, in GCC, I suppose you can use the -s option. So the C files get converted to assembly files and the compiler exits. You can now modify those assembly files to your will and choice. Extremely tricky, but you can still do that. Tricky from the standpoint, the offsets go wrong and this and that, whatever. But if you modify those very carefully and very, with a lot of awareness, then you can take those assembly files and now pass it to the compiler again, saying, okay, now you go ahead and generate the machine code. And yes, you can, optimize them in your specific way. That can be done. Yeah. Cool. So any more questions or comments? If not, I think, well, Rajat's telling me that I should add him back to the call. Yeah, just let me.
And then I
Yeah,
think
are
we
you
can
here?
conclude.
You were able to hear us while you were on the
Yeah.
waiting area? Oh, okay. Okay, any
Yes.
questions?
That is
or
a bug
comments?
or a feature? I don't know.
I don't. We were in full screen mode, so I couldn't see that he's waiting in the lobby. Yeah.
Yeah.
Go ahead.
So
Go
that's
ahead.
so that's why the first thing I bought in the sale is a UPS.
Yeah.
So at least my Wi-Fi doesn't disconnect.
But then we did see you drop off. Did you rejoin from another network or?
No. My light is back up, so it's just like a 10-second cut, but within that time, routers take like 5 minutes, 1 minute to come up.
Yeah.
Right.
But power never goes out in Bangalore, right? Never. I've never seen.
Of
No,
course, of course.
obviously it's free.
Goes sometimes.
Also, sometimes intermittently.
I wonder
power doesn't go
what
there.
architecture the router is running. It takes like 1
ARM
minute.
definitely.
Ah,
ARM.
But
Well,
then the
mostly
one
ARM
question
because. Yeah.
One question is, it should have a small firmware. Why it takes so much time to bring back
Oh,
to the...
to boot up, I think it's.
Radios, I think, take a lot of time. Initializing and
Yes, programming the radios is one, but I think it needs to do a handshake with your ISP again,
yes.
share the credentials and all of that again. Then one
And
by one,
DHCP
each of the
protocol,
devices.
it has to.
Yeah. So you lose the track of you lose the complete track of ISP, right? So whenever you boot up, you need to again go talk to ISP, get the fiber up, and then you have to get Wi-Fi up, which has its own sweet time booting.
Yeah.
And
plus,
then
I think
also,
router
I
runs
should-
Linux, right?
Exactly.
Yes.
It's
Exactly.
not like a
This is what
small
I was going
firmware.
to-
It runs Linux.
It runs Linux.
That takes like few
Oh.
seconds to come up. Yeah, embedded Linux or something like that, typically.
Yeah.
A lot of decisions to be taken, right? A lot of bookkeeping to be done, and like an RTOS, well, you can pull that off in
You
an
need
RTOS.
network stack, and I think
The network
But
stack is quite
which
huge.
firmware
network
is it?
stack.
Like entire
I think
Linux is running? I mean, I don't think so.
And Linux is running.
Yeah,
Typically, yes, because the thing is, if you log into the Wi-Fi over, that 168.192.0.0.1, because it's running something as heavy as, well, not heavy, but a cut down minimal version of Linux, still 10-ish MBs, let's say. The Linux stack has the support for handling incoming requests, presenting a page, all of that. To do the same thing in an RTOS, you would require, well, first off, many engineers who are doing that custom specific thing on an RTOS. But then people figured that, hey, this is already available in Linux. Why don't I just port Linux? So that's typically how it is. At
Plus,
least,
it's not gonna. I mean, RTOS is like, hey, I don't care if a few packets are dropped. It's not as if
well,
someone's
again,
life is
depends,
over.
right?
So
That's true. Like RTOS typically means hard real time. Well, hard or soft real time. I think what you mentioned was soft real time. Dropping packets is all right, UDP, but not always. Life related situations, it's hard real time.
Yeah, it's fine for router to drop packets.
Yeah, okay. For router, yes. But I just wanted to kind of correct the notion of, it's running in
Yes.
RTOS and it's okay to drop packets.
No,
Fine.
no.
But RTOS generally, means that you want it to be real.
no, it is fine, right? Routers can and do
No,
drop
I'm
packets
saying,
if their buffer is full.
yes, of course. In case of the RTOS, in case of a router is soft real time, it's okay to drop packets. Let's do this then. Let's I think we have come far away from the original ISA topic and now drifting into RTOS implementation, this, that. I think we have kind of initially touched upon the fact that for an embedded systems engineer, it's not that you should by heart and know the ISA, at all times, but you should know that it is available. Every CPU has one, depending on what architecture it implements. and it's a good idea to be able to dig into it if the time comes, right? And there are certain operations that you cannot do in plain C using plain C keywords, and in that case you have to hand write the assembly. And yeah, pretty much that is what we wanted to highlight and discuss on as part of this topic. And yeah, I think with that we'll just end it here and catch you people next time.
Yes.
Okay, we can wave our hands
Bye-bye.
and then
If anyone is listening till the end, then thank you.
thank you.
Yeah.
Okay, cool.
Bye bye.
Got it. Yeah.